So welcome guys back again to another video in our inorganic chemistry playlist. So we were talking about our metal centers, molecular orbital theories and complexes. So in this video we are going to talk about the backbonding effect, or we call just pi bonding. That's small difference between those two words. We will talk deep into this. So for our simplicity, I will take an example. Let's take a bond between a metal M and carbon monoxide, right? Okay, so before we are coming into what is this backbonding is all about, I want to show you some small thing about this carbon monoxide. So every ligand has this kind of characteristic in order to go through this backbonding process. So let's go for our molecular orbital diagram for carbon monoxide. So you know carbon, here we have three three p orbitals and one s orbital. For oxygen, same, and one s orbital. So if you can see between the carbon and oxygen, carbon has higher energies. If this is the p, so here carbon has little bit higher energy than the oxygen. Why? Because oxygen has much more tight bonds with our electrons because of the high proton amounts. So that's why oxygen has little bit lower, or oxygen is much stabilized than the carbon when it becomes the molecular orbital. So let's put some electrons here. So oxygen we have like this. Okay, now when we are constructing the molecular orbital diagram for it, I hope you know. So I will just fill it up. So here we have S sigma, and then we have P sigma, and then we have P5, then we have S sigma star, and then we have 5 star, P5 star, and finally we have P sigma star. So let's fill up the electrons. I hope you know how to draw this molecular orbital diagram. If you have not, if you not remember all the stuff, go to our playlist. There is a video about molecular orbital diagrams and how to construct those things. Okay, now this is our molecular orbital picture for carbon monoxide. So if I draw carbon monoxide atom over here, right? So here we have a two electrons and two electrons over here. So I will not draw electrons on oxygen because we are more important on carbon. Like, okay, here's the thing. So you can see there's a empty 5 star orbital which is located just like this. This is vacant, right? This is a vacant 5 star orbital. This is a vacant 5 star orbital, right? So which is, we can show it as this one. So this is very important when it comes to backbonding. Now why I have drawn this molecular orbital diagram is to show the relationship between this one and this antibonding orbital, right? So you need to have some idea about this and just to look at it and just have some idea about it, because we will need this molecular orbital, this representation of electrons, when we are talking more about backbonding. So let me go through the process which is happening. Now here we have the metal center. Now here we have carbon monoxide. So first step what happens is our carbon monoxide will donate its electron density to our metal center, right? Our carbon monoxide will donate its electron density towards our metal center. Now this electron donation will happen through this sigma star orbital. This orbital over here, this antibonding orbital, will donate its electron to our metal center. You can see when this happens, when this antibonding orbital donates electron towards our metal center, our carbon monoxide's antibonding character will be reduced. So in this first step, this is the step number 1, we call it as sigma donation. In this case, carbon monoxide bond will be strengthened. Why? The anti-bonding character is reduced, right? So bond order is increased, which means carbon oxygen bond is increased. So now what's happened? Our carbon monoxide have donated its electron density towards our metal center. Our metal center now have higher electron density, which makes it little bit unstabilized. Now, if this our metal center contains perfectly aligned d orbitals, right? Perfectly aligned d orbitals with our carbon's anti-bonding 5-star orbital. Here, remember this guy over here, this guy is here. So if our metal centers d orbital, mostly like dxy, dxy, dxz, any three of dxy, dxz, and dyz, any three of these orbitals is perfectly aligned with our 5-star orbital, it can start back bonding to our carbon atom to reduce this increased electron density. Now this electron donation from our metal center to our ligand is populating this electron, so this antibonding orbital, which again increasing our carbon monoxide antibonding character is very large amount, by very large amount. So this will reduce our strength of carbon and oxygen bonds. So always remember, when the back bonding is happening, right? When the back bonding is happening, our carbon monoxide bond is weakening, right? If when the complex and ligand forming a bond together, if our metal center and carbon or our ligand making the bond together, only the sigma donation happen. No phi bonding will be happen then, right? Just consider this thing. If our metal center and carbon monoxide is bonding together, not carbon monoxide, any kind of ligand, right? Let's say no phi bonding has occurred, only the sigma donation. Then this carbon monoxide, this bond here, it will get strengthened, not weakened. Why? In the sigma donation, in the first step, this anti-bonding character will be reduced. This electron will be donated towards the metal center. No phi bonding will happen. No population will be happen over here. But if the population happen, if the phi bonding happens, then which means our metal center will donate electron density back to our carbon monoxide again, which will populate our anti-bonding character. Then carbon monoxide will be weakened. You need to have a good idea about that. So step 1 is the sigma donation, and then the step 2 is the phi bonding, or we call it back bonding. Always remember, now there are some factors affecting this back bonding. First thing is there should be a perfectly aligned five-star antibonding, or let's say orbital, perfectly aligned vacant orbital. The orbital should not be populated. The vacant orbital should be present. And again, our metal center should have high electron density. Let's say if we take like Fe3 plus, or likewise highly oxidated metal center which has lower electron density, it will not go pi bonding. Why? It doesn't have enough electron density to back donate to our to our ligand. So high electron density on our metal center is essential for back bonding to be happen. So you need to have this idea. So okay, now with the knowledge we have about our back bonding, let's move forward into more things about our topic. So here we have a molecular orbital diagram for an octahedral complex. I hope you remember about this molecular orbital diagram, which we have discussed perfectly in our previous videos. So if you have not have a good idea about it, I will put the link above so you can go back to it and remember it again. So here we have metal center orbitals and our incoming ligand orbitals. When the bonds forming between our ligands and metal center, right, this is the molecular orbital picture we have. You can see there are 3 orbitals here. Let me take another color. Okay, here we have 3 orbitals which are non-bonding, because these three orbitals, which is dxy, dyz, and dxz, these orbitals do not have a perfectly aligned orbitals to form bonds with the incoming ligand. But if you remember, when it comes to backbonding, right, when it comes to backbonding, these 3 orbitals may have a good perfectly aligned orbital with our ligand's pi orbital, right? So either one of these orbital will go to form a 5 bond with our ligands, one of the 5 orbitals, which will cause to change our molecular orbital picture. So let's move around. So there are 2 cases, right? Case number 1. Okay, here we have our T2G orbital. Now let's say our ligand's phi orbital have less energy, it's much stable. This is our ligand's phi orbital, right? These 2 are gonna form the bonds together. So now 2 bonds will be formed. This is gonna be phi star orbital, which is anti-bonding. This is gonna be phi orbital, right? Okay, so now there's another thing you need to remember. If I ask you what's the gap called between the EG star orbital and T2G orbital, you must know this is delta O, which is crystal field splitting energy, right? You need to have a idea about this. This is very important, right? So when it comes to this molecular picture, when the T2G is forming a bond with our particular ligand's phi orbital, there is our EG star orbital too, right? There is this our EG star orbital too. It doesn't have any effect on this particular bond forming, so the energy will be the same for EG star orbital, right? Okay, now when the bonds are forming, when the molecular bonds are forming, you can see our ligand is much closer to bonding orbital, so it will donate its electron density to the bonding phi orbital. So our metal center have no choice, it has to donate its electron density to the phi star orbital. Now the delta O separation is based on the EG star orbital and the electron density of the metal center. So initially our metal center has electron density on T2G orbital, like in this state, but now when the backbonding happens, the electron density has increased its energy up to this point. Now the delta O will be decreased. Okay? This is our new delta O. Right? This is our new delta O. So in these cases, we call them as weak field case. These are weak field cases. So the ligands which are contributing to this effect to cause to reduce our delta value, we call weak field ligands. So mostly high electron density ligands, such as like chloride, bromide, these are most likely weak field ligands, right? These are most likely weak field ligands. So now let's move into the next step. Our next case is case number 2, right? Here we have our T2G orbital, and it will form a backbonding with the ligand has high energy. So same like they will form 2 orbitals. This is phi orbital and this is phi star orbital. Now our EG star will be here. It won't change its energy level. Now here we have our delta O value. Now what's happened is, when the molecular orbital is forming, our ligand has high energy, our metal center has low energy, so this metal center will occupy our phi bonding orbitals in lower energy level. So our ligand has no choice, it has to go into the upper level. So now look at this. Now the delta O separation is based on the Eg star and the metal center's electron density, right? So now here we have our metal center electron density. So the delta O value will be increased. Now this is our delta value. Sorry, not here. This is our delta value. So delta value is increased. So we call this as strong field case. The ligands particular to showcase this kind of process we call as strong field ligands. Mozilla carbon monoxide, H2O, right? These ligands are we call as strong field ligands. So this is the important thing you need to understand, right? Because that based on the ligand, right? Based on the ligand, this energy can be varied, right? Carbon monoxide, it may have this kind of energy. With water, it may have this kind of energy. For each ligand, it contains specific energy level for its 5 orbital. So which in case when the ligand is changing, this delta O value is changing. That's how we form our spectrochemical series. Right? We have weak field ligands like chloride, bromide, they have a lower strength, and we have carbon monoxide like ligands, we have higher strength. We form this spectrochemical series based on this backbonding phenomena. So when the backbonding happens, this delta O value will be changed based on specific energy level for each ligand. This is the main thing you need to understand. So I hope you have the idea. So hang on, we will go deep into those complexes and its orbitals in next videos.